Students at home, can you hear me? Online participants?
Yes.
Thanks so much. Now I'm going to share my screen and to start today's class. So I would like to focus. Okay, let me start. First, I share my screen. Wait. Let's wait a moment. Okay. Share screen. Next link. Okay. You should now also see my screen. I'm trying to enlarge the screen now. Full screen here as well. Okay, that should be okay, right? Okay, so today I'm going to first show you why for multivariable functions we have different types of chain rule. So today I'm going to present supplementary material, okay? And to focus a little bit more on second derivatives. This part, it's quite reasonable to devote, let's say, 20 minutes to this part today, because we already studied multivariable functions and chain rules. But for multivariable functions, good morning, we have, okay, so let me record the class, of course. Let me record the class. I'm now recording. Okay. Okay. For multivariable functions, we have different types of chain rules. In particular, the type of chain rule that I'm going to present today is really useful for at least two applications. One, when dealing with variables that evolve over time. So we may have, for instance, two economic aggregates, let's say capital and labor, or income, whatever. And the third quantity, which depends on these variables. If the independent variables vary themselves over time, also the dependent variable will vary over time. And in many applications, we need to estimate what is, for instance, the growth rate of the dependent variable, depending on the growth rate, time growth rate, of the independent variables. Okay? So this is a very important tool, very commonly used in economics. And this is what I'm going to present today about the chain rules for multivariable functions. Next, I will show you the very basics of the product between a vector and a matrix. So I will define what a matrix is, what a vector is. And the purpose of this is just that you become able to understand the notation that we find when dealing with multivariable functions in a vector notation, okay? A very typical multivariable function is a quadratic form. This is common in economics, optimization, and also in statistics and econometrics, okay? You must be able to read immediately the structure of a quadratic form, okay? To understand immediately that a mathematical object is a quadratic form and what is its dimension, okay? So this is notation. The purpose of this is to understand quadratic forms, but more details on matrix algebra will be in the second part of the course. Second. And third, introduce second derivatives for multivariable functions, and show you how they can be treated with a matrix notation related to quadratic forms, and basically study concavity and convexity. Not sure I will be able to finish all of this material today. Possibly we will continue next week, because this is strictly related to optimization. Next week we will see optimization without constraints, which is basically finding the stationary points using the first partial derivatives, finding the stationary points of concave or convex functions. We will not deal with more complicated frameworks of optimization. Only concave and convex functions, because this is by large the most common situation in the most common models, okay? So it will be just a matter of understanding whether our function is concave or convex, and then use the first order conditions to find the optimum, okay? So this is basically what we will do. And then next week and the week after, we will deal also with constraint optimization, a little bit more. And then we will have at least 3 hours for summary exercises and examples, basically on multivariable calculus and basic problems of optimization in 2 variables. Remember, I'm just focusing on the main tools, the most common functions. I'm not going to optimize very strange functions that you will never see, you will never use in your studies, okay? Just the most common types of functions. The first topic of today's class is the multivariable functions, different types of chain rule. This is a very important tool. This is also related to dynamics that we will see in the second part of the course. Suppose that you have a function of 2 variables called the dependent variable z. Okay, so suppose that z is the log of f of xy, okay? This is the most common type of chain rule. Z is a function of f of xy. Remember the structure here. The inner function, f of xy, is a 2-variable function, but g is a 1-variable function. So first I compute a 2-variable function, f. Then I transform, this is a number, okay? A number. Then I transform this number by g, and this is the resulting value for z, okay? This is the first type of chain rule, and you know that the chain rule in this case looks like this. The partial derivative of z with respect to x is, first, g prime. This is a correct notation because g is a 1-variable function. G prime computed at the point f of xy. So, means at the point which is the result of f of xy, okay? Times the partial derivative of f with respect to x. Similarly, the partial derivative of z with respect to y is g prime of f of xy multiplied by the partial derivative of f with respect to y. Okay, so this is a straight generalization of the 1-variable chain rule. Okay. Okay, but with many variables, we may have multiple possible structures of chain rules, of course. Not just that the inner function is a 2-variable function and the outer function is a 1-variable function. We might have the opposite. The outer function is a 2-variable function, and the inner function and the 2 arguments, okay, are themselves 1-variable functions. That is another structure, which is precisely the one that I'm going to deal with now. This is specific to multivariable functions. I have a function z, which is now capital F of xy, but x is itself a function of t. T is a unique independent variable that affects both x and y. And y is g of t. Very typically, very often, t is interpreted as time. For instance, z could be a production function that depends on 2 input factors in a dynamic setting, okay? Because the amounts of the input factors depend on the overall performance of the economy, okay? And they are functions of time. it's clear that z, it's convenient to express z as a function of two variables because we have models in which the output depends, that could be also the output of the whole economy, okay? The output depends on the input factors of the economy, okay? So it's very reasonable to express a two variable dependence here, but in a dynamic setting, both of them depend on time. So in principle, z is a function of time. Z depends only on time. Time runs, x and y change with time. On their turn, x and y affect z. Okay? So it's very reasonable to compute the time derivative of z. Okay, this is the chain rule in this case. It is a chain rule because it is a composite function. Compute the partial derivative of f with respect to x and multiply this by the derivative of x with respect to t. Okay? So partial derivative of f times time derivative of the variable plus other partial derivative of f times the time derivative of the other variable. This is the structure. And this is called sometimes, especially in economics textbooks, total derivative of z. Okay? And you see that the total derivative of z, a little bit like the differential, okay? It's similar, the structure. It's the sum of the two partial contributions, okay? So the total derivative of z with respect to time is the sum, it's an additive structure, of two contributions. One is the contribution of x changing over time and affecting partially capital F. And the other is the contribution from y changing over time and affecting f on the other side, okay? So this is the sum of two partial contributions. So this is the basic rule, chain rule, for two variable functions. Each of them depends on time. I don't write the general model here, but it's clear that if z depends on 10 variables, I will have 10 partial derivatives, and I will multiply each partial derivative times the corresponding time derivative, okay? So for 3 variables, that could be x, y, and u, this one, plus the partial derivative of f with respect to u times the derivative of u with respect to time. So it's a general model. So I illustrate this with 2 variables, but it is a general model. So basically, we could also use a matrix notation, but I don't want to introduce this now, but it's a product between the gradient of f and the vector of the time derivatives of the n variables, okay? Okay, this is an example. What is the next step that we will study later is sometimes we don't need to know exactly what is the time derivative of z, but we are interested in the time growth rate of z. Time growth rate means time derivative, divided by z, the value of the variable at time t. And we get a very simple formula which relates the time growth rate of z to the time growth rate of the 2 independent variables, okay? This is the next step. But now an example on the basic formula. Suppose that z, which is equal to capital F of xy, is the log of 1 plus alpha x plus beta y, where alpha and beta are positive parameters. This is a very reasonable function that incorporates, by the way, this incorporates concavity. We will see it later. I'm using this function in these examples. Another function could be the power function in 2 variables, the Cobb-Douglas function. That would be another very sensible example for this kind of models. Suppose that x itself increases over time this way. It's 1/2 t squared. Also, y increases over time, but in a different way. It's a square root of 1 plus t squared. So basically, this explodes quadratically. Remember that time is defined only for t greater or equal to 0. Okay. we don't have negative backward times in economics, at least in economics. So, and this explodes over time, and this increases, but the rate, the slope becomes more and more flat over time, okay? I have to compute the ingredients of my model, so the partial derivative of z with respect to t is alpha divided by 1 plus alpha x plus beta y. It is itself a composite function of x, okay? And this must be multiplied by the time derivative of x, which is just t. Next, plus partial derivative with respect to y, which is beta over 1 plus alpha x plus beta y, times the partial derivative, the time derivative of y with respect to time, which is 1 over 2 square root of 1 plus t squared times 2t in the denominator, because it is itself computed as a chain rule in one variable, okay? Now, what happens here? We have a common, this very often, we have common factors in the two terms, in the two additive terms. So it's very convenient to rewrite this in a better way, not just for to have a shorter formula, but also because sometimes we have to divide this by z to compute the growth rate, okay? So it's very convenient to isolate the common factors here, which is 1 over 1 plus alpha x plus beta y times t, okay? You see it's present in both terms. So I write this, but now, so what is written here is t divided by 1 plus alpha x plus beta y, okay? Why is that? Because remember that we want this, in some cases, we want this to be expressed as a function of time. Remember that alpha x here is alpha over 2 t squared, and beta y is beta times the square root of 1 plus t squared. So this is the common factor here, times alpha plus beta divided by square root of 1 plus t squared. Is that clear? So this is a function of one variable. It's very convenient to regard the structure as a composite function in which there is a direct dependence on two variables, but each of these variables depends on time, and use these chain rules, which allows us to compute the time derivative of z in two steps, and with a very simple structure, additive structure, okay? With the sum of the two contributions. But next, it depends on your application. If you need to express the derivative in terms of time, just remember that the x and y appearing in your derivative are themselves functions of time, and replace and get the final expression, okay? Why is that useful? To understand how useful it is, try to compute the same derivative directly. So you know this model, then you go like this. You know that x is this, you replace this x. You know that y is this one, you replace this y. Then you have your function of t. Now you have to compute the derivative with respect to time, okay? So this is easier than the direct computation. Probably in this case they are somehow the same level of difficulty, but there are some cases in which it's much more convenient to use the structure of composite function. Clear to all? Okay. Of course, this is an exercise, useful exercise. If you compute it directly, you should get the same result. And also, remember that in some cases, we cannot compute them directly. Why? Because we don't have the final expression here for x and y. We just know that x is x of t, y is y of t. If we replace here, we get something which is not really useful. But if we use this structure, we may have at least some idea of the structure of the derivative, okay? Even in general terms. Okay. This is an example very similar to another example in your textbook, okay? So you have one more to practice if you like. Now, in some cases, it's useful to compute the time growth rate, not the time derivative, the time growth rate. I will illustrate this with a specific example in which I have a function which is supposed to be a demand function for a given good that depends on the price of the good and on the income. Very common type of model. Usually we have, you know what a demand function is, I guess so. Demand function is quantity demanded as a function of some variable, in particular as a function of the price of the good. And in more sophisticated models, it depends also on other variables. For instance, in this case, it depends also on the income. This is just a common formula, a plausible, let's say, formula. There is no calibration here. It's just a plausible formula in the sense that the demand decreases with the price of the good, but at the same time it increases with the income, okay? Very reasonable assumptions, qualitative assumptions incorporated in this function. This is a power function in two variables. The power function in P with a negative exponent and in M with a positive exponent equal to 1/2. In particular, when we have these power functions, these kind of computations become very interesting. Suppose that the price itself increases exponentially at 2% rate per unit time, okay? So it starts from the level 5 times 0, and then it is times e to the power 0.02t, okay? This is an exponential model, and the number that you find here, 0.02, is the instantaneous time growth rate of the price, okay? So this is P prime over P. I explained this in the first classes this year course. This is P prime over P. P prime over P, let me just introduce more notation on these time derivatives, because we will use them a lot in the second part. I hope that everybody remembers that if I have an exponential functions of time, exponential function of time like this one, (2% is the time growth rate, okay? It's P prime of t over P of t is equal to 0.02 for exponential functions. Okay. Sometimes P prime of t is denoted as P dot t. This is called a dot notation for time derivatives. Basically, this is the derivative with respect to time. When an independent variable is time, the time derivative is denoted as P dot, okay? This is just a matter of notation. Okay, so let me... Now, suppose that the income increases in this way, so the price increases exponentially, the income in this model increases linearly, it's 100 times 1 plus 0.05t. So basically at t equal to 0, it is 100, then it increases linearly. The demand function, regarded as a function of price and income, is in fact a function of time. If I want to compute the derivative of h with respect to time, the demand with respect to time, I use the basic formula of the chain rule. It's a partial derivative of the demand with respect to price. Look, it is the green the first factor of the green part, it is 2 times minus 1/3 times p to the power minus 4/3 times square root of m, here, times the derivative of p with respect to time, which is just 5. The derivative of the exponential function is the same function multiplied by the time growth rate, okay? So it's 5 exponential 0.02t times 0.02. So this is the green part, is the first additive term. What about the red part? The partial derivative of d with respect to income, so it's 2p minus 1/3 times 1/2 m to the power minus 1/2 times the derivative of income with respect to time, which is exactly equal to, it is equal to 5, okay? So this is constant, so it's 100 times 0.05, which is 5. And this is the first step. Clear? Next step. There are common factors here. Typically, p to the power of minus 1/3 is a common factor here. P to the power of minus 1/3 times, okay, here I have minus 2/3 divided by p, times square root of n, times 0.1, because 0.1 is just 5 times 0.02, okay, 0.1 exponential 0.02t. And if I factor the second term, I get the second additive term, sorry, the second additive term, this one, 2 and 2, I can simplify 2 and 2. P of minus 1/3 is a common factor with the previous term, so I get 5 times 1 over square root of n. This one. This is a slightly more reasonable way to write the result. P and M are given by, of course, their definitions in terms of time. So in principle, it depends on what you have to do, but in principle, you should replace here P as a function of time, P as a function of time, M as a function of time. So it's a very long formula, okay, for the result. But here you see the structure, which is much more convenient. Now I want to compute the time growth rate, the rate of growth, which is not the rate of change. The rate of growth is the log derivative. So basically it is the derivative time derivative divided by the function. Divided by the function. So it is derivative of d with respect to time over d. Why is that useful? Look at this common factor here. It is also present in the function, okay? So you will have a lot of simplifications here. Okay, so divide this by the function, which is, it is this formula, 2 square root of n p to the power minus 1/3. Okay, this disappears, and you have in the denominator 2 times square root of n. Okay, so it becomes a lot easier here. It's minus 1 over 3p, square root of m disappears because it is in the denominator, times 0.1 exponential 0.02t, plus 5 over 2n. And this is much more reasonable. But this structure that you see and this possibility to simplify is not just by chance. It is a general property that we are going to possibly also to show you in at least two lines of computations. It's very easy to show this. That the the time growth rate of the dependent variable, which is the demand in this case, d dot over d or d prime over d, is just the elasticity, the partial elasticity of the demand function with respect to price. Okay. Is that the microphone? Okay, let me check one thing. Can you all hear me?
Yeah, but it's quite noisy.
It's quite noisy also here as well. Okay, so my speaker is mute, so let's wait 5 seconds. No, I have to just wait a minute. But basically this is the formula, okay? Okay, it's coming in a minute. Let's just continue these conditions and then let's hope the best for the future. Okay, so this is basically the structure of our formula. If you are interested in the growth rate of the dependent variable, the formula, the additive formula, relates the growth rate of D to the growth rates, time growth rates of the two independent variables. In this way, the time growth rate of the price times the partial elasticity of D with respect to the price, plus the time growth rate of the income times the partial elasticity of the price with of the demand with respect to the income. Okay, so this is a very interesting formula because often in application we are interested in growth rates, and this is, I mean, also the proof that elasticities are really important in this kind of models. Okay. So the elasticities are, partial elasticities are quite important sensitivity measures. Oh, this is the proof. Prima era più forte, adesso fa così. Non vorrei fosse il microfono, forse è il microfono di qualcuno a casa? Il mio, di quello che io uso per entrare, è spento. Io lo adesso si sente meno. Ha cambiato qualcosa? Oh, okay. Qual è? Così se ricapita lo faccio.
No, era qua per del mezzo, invece...
un po' spostato, però prima andava bene all'inizio.
Dopo un po' fa... No, come faccio?
Okay, so grazie. Okay, this is the proof of this. Okay, we know that the time derivative is the partial derivative of d with respect to p times p dot, the time derivative of the price, plus the partial derivative of d with respect to m times m dot. Okay. No, this is don't look at this. What is written here in this bracket? P dot is just the derivative of price with respect to time. M dot is the derivative of income with respect to time. Sorry, there is a mistake here. Okay. P dot is the time derivative of the price. M dot is the time derivative of the income, not over P, not over M. But now try to divide D dot by D. Okay. If you divide D dot by D, you just put D in the denominator of both here, okay? Now, so you have two terms, two additive terms, the blue ones. Don't look at the red parts now, the blue ones. Just divided this one by D. Now, multiply and divide each term by the same quantity. The first term is multiplied and divided by P, which is in red here. The second term is multiplied and divided by M, which is in red as well. Now look at the new formula. This part is the partial elasticity of the demand with respect to price. It is now multiplied by P prime over P, which is the time growth rate of the price. The second term is the partial elasticity, this one, of the demand with respect to income, which is multiplied by the time growth rate of the income. Okay, so it's very easy to prove this in general. In particular, if our function is power, if our function D, that depends on price and income, is power function, it is, in our case, it's multiplicative constant times the power of the first variable times the power of the second variable. Okay? If it is power, these elasticities are constant. Okay? Because the power functions in two variables have constant elasticities. And they are equal to the exponents. So the two partial elasticities are minus 1/3, 1/2. Okay? So the formula becomes even easier for a power function. That would be the first exponent times P prime over P, plus the second exponent times M prime over M. So in our example, we have P prime over P is 0.02. M prime over M is what? Okay, M is a linear function of time. The intercept is 5. So M prime is 5. M dot is 5. Over M, M is the income itself. The partial elasticity of the demand with respect to P is minus 1/3. With respect to M is 1/2. Because it is an isoelastic function. So the formula that we expect to see from this general structure is just this one. Minus 1/3 times 2 over 100. 2 over 100 is 0.02. Plus 1/2 times the time growth rate of the income. And this is, I mean, I don't want to you can check immediately that this is the same result obtained above without knowing this property. Okay, it's just performing all the computations. It is the same result obtained above because we can have a look at it. We obtained this one, okay, but remember that P is 5 times the exponential of 0.02t. Okay, so we have a big simplification here. And also M, we have to replace to M its expression. And this formula, denoted by a triangle here, if you work it out a little bit more, replace price here with this expression, which is an exponential function, replace the income with this expression, you get exactly this one, which is the formula that we would obtain immediately by applying the general property, okay? sum of the elasticities times the time growth rate. Okay, so this is the steps. Okay, the price is itself an exponential function, so it can be simplified with this one. And final step is this one, which is precisely the formula here. Okay, this is just a algebra. Okay, so we did this because it is a very meaningful example, a very significant, a very meaningful example because it's very typical. We suppose not to know the property, and we try to compute the time growth rate of the demand just by using the definitions, and then we apply this property to check that the result is the same. So this is really, really important. Now, you may also wonder, this is just the last example, you may also wonder why we call this the total derivative of Z. And the next example shows why we call this the total derivative. It is intuitive that this is a total derivative. It is the sum of two partial contributions. And these are partial derivatives. But these are partial derivatives of Z with respect to the two variables, not with respect to time. But there is a typical example which falls within this structure, but it is more simple, which is this one. Suppose that you have a function of two variables, and the dependent variable is called y, and it is a function. It is itself a function of time. Okay? And it is also a function of another variable, k, which on its turn is a function of time. Okay? This is, for instance, some production functions with exogenously changing technology have a direct dependence on time because the technology improves over time, and have an indirect dependence on time because they depend on the capital stock, which itself changes over time. Okay, so this is a typical example, which is in the next slide. Now, is that similar to the previous case? Yes, it is similar, and it is even easier. Why? Because I can regard this is our previous Z, okay? The dependent variable depends on two variables, and both are functions of time. K is a function of time. T is itself a function of time. It is the identity function of time. It has derivative equal to 1. So I can apply the previous formula. So if I want to compute the derivative of y with respect to time, because y depends on time, in this case it has a direct dependence and an indirect dependence. I have to compute the partial derivative of y with respect to its first argument. So it's partial derivative of y with respect to time, times what? The derivative of the first argument, t, with respect to time, which is 1, plus the partial derivative of y with respect to its second argument, which is dy by dk, times the time derivative of k, which is this one. So it is the same formula as above, but it is easier. And this is the reason why this is called the total derivative and this is the partial derivative. Because now, on the left side, you have the total derivative of y with respect to time, total time derivative of y. On the right, you have another derivative of y with respect to time, which is not the total derivative. This is the partial time derivative of y, okay? So on the right, you have partial time derivative of y that captures the indirect dependence of your variable y on time. On the left, you have the total derivative that captures the sum of the indirect this captures the direct dependence. Partial time derivative captures the direct dependence, but there is another term, which is the indirect dependence, and the left term captures both. So this is the reason why this is called total time derivative, and this is the partial time derivative of the same variable. And these models are very common when we have, for instance, this is not the only case, of course, because they are mathematical models. Okay, we may have, just let me finish this part. We may have, this is a very typical type of production function regarded as the output is a function of just one variable, which could be regarded as capital stock of the economy, or more commonly when there is a unique variable, this is the ratio between the capital and the labor, okay? It's a capital per unit of labor. It's regarded as a unique input factor. These are called intensive production functions, by the way, okay? So there is an indirect dependence on time because K is supposed to change in this way, okay? 8 plus 0.05 t squared. So it increases over time. But then there is also a direct dependence because the coefficient here that multiplies K is not a constant like in common production functions, A, capital A. But capital A changes over time. For instance, capital A, this multiplicative factor, now changes exponentially over time. That could be, for instance, a way to model the technology that increases the level of output for a given level of input, okay? And the technology increases over time. The impact of the technology increases over time. So, direct dependence, indirect dependence. The partial derivative of y with respect to t is the partial derivative of y with respect, the total derivative of y with respect to t is the partial derivative of y with respect to t times 1. And this is just the partial derivative of y with respect to t, 0.02. Remember that now I have to regard this one as a function of t and k, okay, because we are applying the chain rule. So don't worry about the fact that k depends on t. This will be considered in the second term. But now this is just a function of two variables, t and k, and you are computing the derivative, partial derivative, with respect to t. So it's 0.02 times 5 times the exponential 0.02t. This is like a constant multiplicative factor times k to the power of 1/3 plus. Now the partial derivative of y with respect to k, which is 5 over 3 exponential 0.02t times k to the power minus 2/3 times the derivative of k with respect to t, which is 0.1t. Okay? Try to understand these structures because they are really common. So, there is a common factor here, which is 5 exponential 0.02t times k to the power 1/3. And now I have into the square brackets 0.02 for the first term and 1 over 3k 0.1t as the second term into the square brackets. This way of rewriting the result is not by chance. It is just because if you won't compute y dot over y, you have to divide by y, but y is this one, and it is precisely what appears here. Okay? So the time growth rate of y is this one. And this is, I mean, it is very, if you look, suppose that you want to compute the time growth rate, so you have to simplify by this disappears, and you are left with the part into the square brackets. Now the part into the square brackets is 0.02, 2% per year, per unit time, plus something that depends on time. Depends on time and on k, the level of k. Of course, here you should replace to k its expression, which is this one. So you have 0.02 plus another part that depends on time. And if you look at the original model, you see that the model has two factors. Here. It's a multiplicative model there is one factor that increases by 0.02 and another factor having its own time growth rate. And this is reflected into the result, okay? So time growth rate of y is 0.02 plus basically the time growth rate of the other factor. So when you focus on time growth rates, you transform, this is not the first time I say that, you transform a multiplicative model into additive growth rates of the two factors. This is another example. Okay, so just keep in mind that these kind of models in which you apply the chain rule to functions like this one, with simple functions, of course, simple functions, elementary functions describing each building block of the model, of course. And with this one, in which we have a true dependence on two variables, with the request to compute, the request to compute, for instance, the time growth rate of the dependent variable or the time derivative of the dependent variable, these would be possible exercises for two variable functions, okay? So this is another type of chain rule that you should care most about these models. Now, the second step of today's class is a basics of matrix notations and matrix products. Really basic stuff. You may know already these tools. Anyway, just to recap what is needed now for notation, basically for the notation concerning the multivariable functions. So it's just I will introduce a notation for matrices and the most simple type of product, which is the product between two vectors and the product between a matrix and a vector. Okay, so what is a matrix? A matrix, like for instance our object capital A, is an array of numbers with a certain number of rows. In this case we have two rows and a certain number of columns, okay? This is called a square matrix because the number of rows, which is 2, is equal to the number of columns. But we could have as well 2 rows and 3 columns, or 3 rows and 2 columns, and more structures, okay? This is called in particular a square matrix of order 2, or a 2 by 2 matrix. It has 2 rows and 2 columns. Another important matrix, a first important operation involved in this matrix is computing the transpose of the previous matrix. So the transpose of matrix A is another 2 by 2 matrix in which I've just exchanged the rows with the columns. So what was previously the first row, now it is the first column, and the second row is the second column. Okay? So this is a transpose of A, and transposition means exchanging rows with columns. Okay, let me now show you another thing which is basically useful to see now. Look at this matrix. This matrix has this property. Of course, in general, this is a general definition. You see, if it is a square matrix, in the square matrix, like in a square, we have a diagonal, right? So this is called the main diagonal. We don't have such diagonals in generic rectangular matrices, because if you have 3 rows and 2 columns, you are not able to identify the main diagonal, okay? This is the main diagonal. In this particular matrix, you see that the elements that are in symmetric positions with respect to the main diagonal are equal to each other. What is the meaning of symmetric positions? This is the element in position 2, 1, 2, okay? First row, second column. This is the element in position 2, 1. Second row, first column. Okay? So the element in position 1, 2, which is denoted by A1, 2 in general, is equal to A2, 1. And this is the only element, these are the only elements outside the main diagonal. This is called a symmetric 2 by 2 matrix. And for a 2 by 2 symmetric matrix and for a general symmetric square matrix, what is the property to define this? This is easy. I could define this by this property, but this is just a 2 by 2 matrix. I want to have a definition in general. If there are 10 rows and 10 columns, I should list all the equalities between the elements in symmetric positions with respect to the main diagonal. We don't need to do that because the definition is that the transpose of A is equal to A itself. If you exchange the elements A1, 2 and A2, 1, okay, and they are equal to each other, and this happens for any other elements that are in symmetric positions with respect to the main diagonal, you can just say that the transpose of A is equal to A, and this is the properties that defines a symmetric matrix, okay? So this is the definition of a symmetric square matrix. Square, we don't need to specify square because it is implicit in the definition, okay? If this definition holds, it must be square matrix. So this is the definition of a symmetric matrix. This is a 2 by 2 example of a symmetric matrix. If you want to see a 3 by 3 example, it's just like this. A is symmetric, could be like this. 3 minus 1, 0. 2 minus 3, 2. Then this must be equal to this one, 2. This must be equal to this one, 2. And this is minus 3, okay? The element position 1, 3 is equal to the element in position 3, 1. The element in position 2, 1 is equal to the element in position 1, 2. And also these elements are equal to each other. So basically we have A 1, 3 is equal to A 3, 1. A 2, 1 is equal to A 1, 2. And then we have A 3, 2 is equal to A 2, 3. All the elements in symmetric positions with respect to the main diagonal are equal to each other. This is a symmetric 3 by 3 matrix. I mean, try to compute the transpose of this and you get the same matrix as the initial matrix. Okay? Okay. Now, go back here. Product between two vectors. Vectors are particular types of matrices. They have this characteristic are matrices with only one row or only one column. For instance, these two, denoted by X and Y, underlined. X is 1, 2. It has 2 rows and 1 column. Y is minus 1, 3. It has as well 2 rows and 1 column. These are called two-dimensional column vectors because they have 2 elements. It is possible to, it is defined an operation between vectors which is called the product in terms of matrix product between vectors, okay? And in order to compute the product between these 2 vectors in a matrix product fashion, we have to replace X with its transpose, a row vector, Y remains a column vector, and then the product X transpose times Y is 1, 2 row times minus 1, 3 column is the first element 1 times minus 1 plus 2 times 3, it is equal to 5. This is the product between the 2 vectors X and Y using the notation of the matrix product, because this will be also the definition of the product between 2 matrices. Of course, the product between 2 vectors is a commutative operation. It has a commutative property, because if I compute the product between Y and X, which is Y transpose times X, I write minus 1, 3 times 1, 2, which is again 5, okay? Because it is the sum of the same terms. Remember, the product between vectors, and more generally, the product between matrices is performed row by column. We have to multiply each row of the first matrix by each column of the second matrix. In this particular case, we have 1 row, 1 column. The result is a scalar. What is the name of the meaning of scalar? When we are dealing with these objects, matrices, vectors, and we have a real number that is the result of these operations, or it is something that interacts with these objects, but we want to distinguish between numbers and matrices, we call the number, the real number, a scalar. So this is a scalar. So remember that the result of the product between 2 vectors is a scalar. It's not a vector. It's not a matrix, if the product is performed in this way, row by column. Now, please don't get confused about that. Sometimes you see the product expressed in this way, X times Y, because it's clear what the product is. We want to multiply element by element, okay, the entries of each vector. So we can just write this in this way, X times Y, which is not the product of a column by a column, which is, it is not possible with the matrices to compute the product between a column vector and another column vector. Not possible. This is called the dot product. So the result is the same, because it is, again, 1 times minus 1 plus 2 times 3. But it is another kind of operation, defined in a different way, having different properties, which is useful to have as a separate type of operation between 2 vectors. This is called the dot product of X and Y, or the inner product of X and Y. In blue, I wrote, this is an alternative representation of the product between 2 vectors. It is useful to have both, because this is something that is useful for certain applications. This is useful when we deal with vectors as special types of matrices. Is that clear? But in practice, the result is the same. Then we have another operation, which for the moment is matrix by vector. We will deal with matrix by matrix in the second part of the course. This is matrix by vector. Suppose that you have a matrix square matrix in this case. So -1, 4, 0, 1. And you have the column vector 1, 2. Now remember, the product between matrices in general is performed row by column. Listen to this important message. Don't regard matrices as arrays of numbers. Regard them as column vectors, for instance, this one and this one, side by side, or row vectors, one over the other, okay? Don't regard this as just the 4 numbers in a square. Look at the vector structure inside a matrix. This is, you can regard this as 2 row vectors or 2 column vectors. This is a very useful perspective on matrices because it helps a lot with matrix operations and to interpret the result. So regard this, if you want to multiply A times X, regard this as 2 rows, okay, and this by a column. We know how to multiply a row by a column, and the result is a number. If we have 2 rows, the result is not a number, we have 2 numbers, one for each operation. First row times the vector, or second row times the vector. You put the 2 results into another column vector, this one, okay? And this is the product of the matrix by a vector. So for instance, the first entry of the result is -1 times 1 plus 4 times 2, which is 7. The second element of the result is 0 times 1 plus 1 times 2, which is 2. And this is the result. We have just multiplied separately 2 rows by the same column, and this is the result. It is a 2-dimensional vector as well. Now look at this other example. And this is a general property, okay, but we'll focus on this later. When you want to, if you have a matrix product and you want to figure out what the structure and the dimension of the result will be, and whether this product is possible, just look at the structures of the 2 factors. This is a 2 by 2 matrix. This is a 2 by 1 matrix. Okay, it's possible to perform the product because 2 here is equal to 2 here. The number of columns of the first factor is equal to the number of rows of the second factor. What will be the dimension of the result? Take the outer terms, 2 and 1. It will be 2 by 1, okay? This is the dimension of the result. Now, first, let me just show you an example with a 3. What about multiplying A times B, where A is equal to 1, 2, minus 1, 0, 1, 3, 4, 1, 0, and B is equal to 2, 0, 1. A times B is equal to, so regard them as rows. It will be 3-dimensional vectors with 3 entries. The first entry is 1 times 2, which is 2, plus 2 times 0 is 0, plus minus 1. 2 minus 1 is 1. The second entry is 0 times 2, which is 0, plus 1 times 0, which is 0, plus 3 times 1, 3. Third entry will be 4 times 2, 8, plus 0, plus 0. Okay, so this is the result of the product. 1, 3, 8. Now, go back here. And already here, no more commutative property. Or here we have a commutative property holding, but it's enough to switch to the product between a matrix and a vector, and we don't have any commutative property anymore. Because if we multiply, instead of multiplying A times X, we multiply, let's say, X times A, which is a row X transpose times A. This is the same X as before, transpose times A. Now what is the dimension of the result? Okay, I can perform the product between, this is 1 by 2, this is 2 by 2, so 2, number of columns of the first factor is equal to 2, number of rows of the second. The dimension of the result will be 1 by 2, whereas before we had 2 by 1, but it is not the same vector, because now we have 1 times minus 1, which is minus 1, plus 2 times 0, and the first entry is 1. Next we have 1 times 4, plus 2 times 1, which is 6. So it's a totally different result. It is not the transpose of the previous one, okay? Why? Because we are performing the product row by column. So the dimension of the result will be different, but also the entries in general will be different. Of course, there are some cases in which you get the same result as a transpose, but they are particular cases. However, so you see that if I multiply A times X, if I put X before A, of course I have to transpose it, and I perform the same multiplication, I get a different result. But, however, A times X is almost the same as, look at this, A times X. I want to multiply X first, so X times A, and I transpose both, so it is X transpose times A transpose. If you do that, you get the same vector as before, which was 7, 2 column. Now it is 7, 2 row. Okay, so the property is general. Okay, you have A times X. The result is a vector. Okay, if you take the transpose of the result, this is the same result that you would obtain by multiplying X transpose times A transpose. This is another important property, because very often we have a model in which we have operations between matrices and vectors, and then we have to transpose it. Okay, so we don't need to transpose the result. We just, we know already A times X. We don't need to compute again X transpose times A transpose. Just transpose the result of the previous computation. This is the operational meaning of this property. Okay, this is a general property for matrices. So let me recap what are the important things here. What is a matrix? What is the transpose of a matrix? The existence of the so-called symmetric matrices, for which the matrix square is equal to its transpose. The product of two vectors with two alternative notations. The matrix notation, the two vectors must have the same dimension, of course. If you use the matrix structure, you have to transpose the first factor times the second. Because product between matrices is row by column, okay? Alternatively, you can denote it as X times Y, but it is another operation which has the same result, but it has a different structure. It is called a dot product of the two vectors. The second step is matrix by vector. Remember that here the commutative property is lost in general. AX is possible here. XA is not possible at all. You can compute X transpose A, but the result is not the same as AX. But if you compute AX, and if you want to invert the two factors, you have to transpose both to get the same result, okay? And what you get is not AX, which is a column, is AX transpose. It is the corresponding row, okay? Is that clear? Look, this part on matrices, how many of you know matrix algebra already? All of you? Oh, all of you, very good. So it is very useful to just recap this, but these are the basic properties. And this is the last part of this introductory introductory notation, which is vector by matrix by vector. So in general, what is really important for matrices, there is nothing difficult in general. It's only a different perspective. You have to manipulate objects that are not numbers, okay? So, and don't regard operation between matrices. Try to understand a little bit more the structure of these operations. So focus on the objects as a whole entities, not just as arrays of numbers, because otherwise it's difficult to see immediately what the likely result of an operation is. For instance, in this case, this is a typical example. And these examples were recommended by professor of econometrics, of course, because these kind of models are very common in statistics and econometrics. It's a vector by matrix by vector. So we find very often this notation X transpose times A times X, where A is a matrix and X is a square matrix. A is a square matrix, and X is a vector, could be a vector of numbers or a vector of variables. Okay, so when I see this notation, look at this notation in red. X transpose times A times X. Okay. So what is the priority of these operations? You already know that with matrices, the priority is important, okay? Because it's a matter of not all the products are possible. There must be some requirements on the dimensions of the matrices. It's clear that the priority is important. So do I have to multiply first X transpose times A and then take the result by X? Or vice versa, do I have to multiply A times X and then left multiply by X transpose? Okay, is that the point? It is indifferent, because if I multiply X transpose times the product between A and X, I get the same result as by multiplying X transpose by A first and then the result by X. Why? Because it is a property that holds also for matrices, which is called associative property. It holds also for numbers, okay? So there is no need to establish a priority here. Any of the two possible priorities is reasonable. I mean, it leads to the same result. And the result of this operation, remember, the result of this operation is a number or a scalar. It's not a matrix. Why? Just look at the previous example. In the previous example, we had A times X was 7, 2, the result. Now, imagine that we want to left multiply by X transpose, which is 1, 2 row. The result here is already a vector. So if you want to left multiply, again by 1, 2 row vector, X transpose, you get 11, okay? This is the reason why this is a scalar, because AX is already a vector, and if you left multiply by X transpose, row vector by column vector, we know already it is a scalar. Okay, In particular, if matrix A is a symmetric matrix, what is the definition? It is equal to its transpose, or for short, the element in the position Aij is equal to the element in the position Aj. I can exchange the index of the row with that of the column for any Ij. So if A is symmetric, X transpose times A times X, it is called a quadratic form whenever it is regarded as a function of the vector X. So here X is not just a vector of numbers, it's a vector of variables, x1 and x2. So when we have this vector by matrix by vector structure, in which the matrix is square and symmetric, and the vector is a vector of variables, having the same dimension of the matrix, 2 by 2 matrix means a two-dimensional vector, then the result of this operation is called a quadratic form. Let me show you first an example in which, another example in which X is just not a vector of variables, but a vector of numbers. Multiply first A times X. I get 2 plus 4, 6. 2 plus 6, 8. Now left multiply by vector X, which is 1, 2 in this case. The result is 6 plus 16, 22. Now do the same with the same symmetric matrix, but not the vector 1, 2, a generic vector X, x1, x2. What we did before is to multiply A times X first, okay? Do the same here. I get, you see, the result is a two-dimensional vector. I have to obtain the same structure of the result. It is 2x1 plus 2x2, the first entry. The second entry is 2x1 plus 3x2. This is the second entry. Now I have to multiply this, left multiply, by x1, x2. And what I get here, don't get confused here, it's the first entry times the first entry here, plus the second entry x2 times the second entry here. Here it becomes clear why it is called quadratic form. Because the two variables x1 and x2 will be either squared in the result or with a mixed term x1, x2. So it is a quadratic expression in x1, x2. So I have 2x squared 1 plus 2x1, x2 plus 2x1, x2 again plus 3x2 squared. So it is 2x squared 1 plus 4x1, x2 plus 3x squared 2. This is called a quadratic form in the two variables x1 and x2. It is a quadratic expression in x1 and x2 without any linear term and any constant term. In this polynomial in two variables, any term has degree 2. This is x1 to the power of 2, this is x1, x2, and this is x2 to the power of 2. This is an example of a quadratic form. How do we obtain a quadratic form? We have a symmetric square matrix. We both left multiply and right multiply by the same vector of variables. The result is a quadratic form. Okay. So look at the result. This is the result. There is a pure term in x1, pure term in x2, both squared, and a mixed term, okay, in x1, x2. Look at the coefficients. The pure term in x1 has 2 as the coefficient. You can see the coefficient in the matrix, 2 here. x1 squared means position 1, 1, okay? 2 is here. x2 squared means position 2, 2, and 3 is here. And the mixed term is the result of the sum of two mixed terms here. So you have to, if you look at its coefficient in the result is 4, is double the coefficient of the, which is not in the main diagonal here, okay? So basically 4 is 2 plus 2, or twice 2. So basically there is a 1 by 1 association. This is if you know the structure of the result, you immediately know the starting matrix. If you know the starting matrix in a quadratic form, which must be symmetric, you know already the coefficients of the result, okay, without performing the computations. So why is that? Because if we, this is the last slide before the break, we have a general matrix 2 by 2. In a general matrix 2 by 2, we have the elements that are denoted as A11, A12, A21, A22. In particular, this is a symmetric matrix, so our A12 is equal to A21, okay? Because in this model we have a symmetric matrix. X transpose times A times X is x1, x2 times our matrix times x1, x2 column. First, I multiply this by this, okay? It is A11 x1 plus A12 x2, the first entry of the vector, which is the result of this product. A21 x1 plus A22 x2, this is the second entry. Then I have to multiply it again by x1, x2. So it is x1 times this plus x2 times this. What is the result? A11 x squared 1, and A11 is here, plus twice A12 x1 x2, twice the mixed coefficient here, okay, plus A22 x squared 2, and A22 is here. Just one more thing. What would you arrive at? What would you write down immediately, the result of this product? So this is again X transpose times A times X, where A is 3 by 3 and symmetric. So it is what is the meaning of symmetric in this case? This element is equal to this one, so A transpose equal to A. So this means that this element is equal to this one. This A13 is equal to A31, and A23 is equal to A32. So if you exchange the index of the row with the index of the column, you get the same element, the same value. And the result would just be so A11 x squared 1, okay, plus A22 x squared 2 plus A33, sorry, this is x squared 2, plus A33 x squared 3 plus, okay, now these are the three pure terms. Now we have all the possible mixed terms, which are in number of 3. So basically one will be of the type x1, x2, the other x2, x3, and the other x1, x3, okay? So plus, look at the term x1, x2. What will be its coefficient? 1, 2, twice a12, which means a12 plus a21, okay? Because it is symmetric. Plus, twice a23, x2, x3, plus twice a13, x1, x3. It is a useful exercise on the matrix product it's clear that this extends the previous formula. Do not trust, just compute the result. Okay, so compute this by this and then times this, then collect all the similar terms and get the final result. Okay, good. So let's take a 15 minutes break. Okay, let's take a 15 minutes break and see you again here at 11. At 11. Okay, we start again. I'm going to share my screen again. Okay. Okay, so share my screen again. Okay, so this is part of the slides, I guess, last week's slides, and we didn't introduce second partial derivatives. We do that now. This is really easy. I mean, like for one variable functions, we have the second derivative. For multivariable functions, we have the second derivatives. They are, of course, second partial derivatives. Why is that? Because the first partial derivatives, which we already know, generally, they are themselves functions of two variables. I'm dealing with functions of two variables, but in general, they are themselves functions of n variables. And for sufficiently regular functions, which is 100% of the functions that we will introduce and we will see in our course, we can also compute the second derivatives, which are the partial derivatives of the first partial derivatives, okay? So, look at the notation. We have the function of two variables, which is f of xy. The partial, consider for instance the partial derivative with respect to x, okay? df by dx, which is itself a function of xy. Now, if it is a function of xy, I can compute two partial derivatives of this function. So in the second step, I will have two partial derivatives of the partial derivative with respect to x. So for each first partial derivative, I will have n additional partial derivatives at the second level. In this case, 2. What about the notation? If I want to express the partial derivative of this with respect to x again, basically, look at the, if you want to understand the notation, look at the partial derivative operator. This is d by dx, is the operator partial derivative with respect to x of something which is into square brackets here, okay? Into square brackets, we have the partial derivative of the function with respect to x. Now, we immediately understand the notation for the second derivative. You see, d is twice here. So d squared, it's not a square, just twice. D squared f by dx squared. Okay? This is the second partial derivative with respect to x, or computed twice with respect to x. Or, it is also called pure second derivative with respect to x, because I compute derivative with respect to x at the first stage and also the second stage. Now, start from the same partial derivative with respect to x. I want to compute the partial derivative with respect to y. This is the operator partial derivative with respect to y applied to what? This two variable function, which is the partial derivative of the function with respect to x. And this justifies the notation d squared f by dy dx, okay? This justifies the notation. If you do the same, and this is just 2, second derivatives. We have two more, because we have to start from the partial derivative with respect to y now. I don't explain everything here. Start from the partial derivative with respect to y. It is a two-variable function. Compute its two partial derivatives with respect to x and with respect to y. This is called the pure partial derivative of f, pure second partial derivative of f with respect to y, because it is computed twice with respect to y. And this is computed with respect to y in the first step and with respect to x in the second step. D squared f by dx dy. Now, example. Cobb-Douglas function. Capital A times x to the power of alpha times y to the power of beta. First derivative with respect to x is a, capital A, times alpha x to the power of alpha minus 1 times y to the power of beta. It is itself a function of two variables. Let's compute the two second derivatives with respect to x again, and then with respect to y of this one. D squared f by dx squared, the pure second derivative with respect to x, is the derivative of this one with respect to x. It is capital A times alpha minus 1, okay, times x to the power of alpha minus 2, and then times y to the power of beta, because in the second, both in the first and in the second derivative, we don't take any derivative with respect to y, so it remains the original constant factor y to the power of beta in both the first derivative and the second derivative, you see? Now I want to compute d squared f by dy dx, which means with respect to x in the first step, so I start from this one, but in the second step with respect to y. Now it depends on y, okay? This is regarded as a function of y. So capital A times alpha times x to the power of alpha minus 1 times beta times y to the power of beta minus 1. These derivatives that are computed in the first step with respect to one variable and in the second step with respect to the other variable are called mixed second derivatives. Mixed. Why? Those computed at each step with respect to the same variable are called pure. Okay? Pure second derivatives versus mixed second derivatives. Okay. Is that clear? If this is clear, this is just an exercise, so I can skip this. I mean, this is the partial derivative with first partial derivative with respect to y, which can be differentiated again partially with respect to x and y. So if I compute d squared f by dx dy, I must compute the derivative of this with respect to x. So it is alpha beta times alpha x to the power of alpha minus 1 times y to the power of beta minus 1, because this is considered as a constant factor in this derivative. And then if I differentiate this twice with respect to y, which means computing the derivative of this with respect to y, it is alpha times beta times x to the power of alpha times beta minus 1 y to the power of beta minus 2. Now look at the mixed second derivatives. Here it is d squared f by dx dy, and it is this one. Here it is d squared f by dy dx. So it is the order of differentiation is inverted, okay? Y in the first step, x in the second, versus x in the first step, y in the second. But the result is the same, okay? This is not obvious at all, a priori. I mean, the result is the same. It holds for basically any sufficiently regular function. This is called Young's theorem. It just states that when you compute the second derivatives with respect to a given set of variables, the order of differentiation doesn't matter. So the result is the same. So the mixed derivatives, if computed with respect to the same set of variables, are the same. While the pure derivatives are different. Now, the geometric meaning of the pure derivatives is quite standard. I'm trying to illustrate this. If I can go back to this curve here. Oh, that's good. You remember the meaning of the first derivatives I've shown previously. Computing the first derivatives means just computing slopes along some directions. There are two main directions, the red one and the blue one. You see that, in fact, I'm computing the slopes of, not of a surface, of a curve, because along the red direction, it's like having this curve on my surface, okay? It's just a curve. So I'm computing the slope, the slope of the tangent line to that curve at that point. Now, in this particular picture, not only this is the slope of the tangent line, but the curve, the red one, is also concave. You see, it can be regarded as a concave function of one variable, okay? Why one variable? Because only x is changing here, because y is fixed at the level y0. Okay, if this section is concave, you should expect that the second derivative is negative. Which second derivative? The pure second derivative with respect to x, because I'm just keeping y at a fixed level. So this is just a function of x. If the pure second derivative is negative with respect to x, then you can see it from the graph. Okay, my function, my section, is a concave curve, concave function of one variable. And also in this picture, also the second pure derivative with respect to y would be negative in this particular graphical case. The meaning of the mixed derivatives is not that intuitive. So the pure derivatives is just concavity or convexity along the two main directions. The same directions we compute the first derivatives. Okay? The meaning, geometric meaning of the second derivatives is not that is not intuitive at all. It has to do with the behavior along the other infinitely many directions, basically. So don't worry about the meaning of the mixed derivatives, but they will be useful to characterize concavity for a multivariable function. Because I don't know whether this is clear from this picture, but having, for instance, concavity here along the two main directions is not enough in general to having a concave surface, okay? In this case, this picture looks like being concave along all the other directions. It's like this, okay? At least in this part of the graph. But it's not always the same. I mean, you may have concavity along the two main directions, but a strange behavior along the other directions, okay? I'm not sure it is intuitive, but it is quite easy to have examples of this. And so you would have convexity along the other direction. Think, for instance, you know, a horse saddle, okay? It's like this. This is the part on the back of the horse, and this is part on the sides. So this is concave in this direction, convex in this one, okay? This is a saddle behavior. That would be a saddle behavior along the transverse directions, something like this. Anyway, in this case, the surface is clearly from the picture concave, and in particular, it is concave. Concavity emerges from the sections along the main directions. But in general, that's not true. I mean, having the two pure derivatives, both negative, is not enough for concavity. Because it depends on what happens along the other directions. Don't worry if you don't get the geometric image. But I would like you to do that as an exercise now, not now, maybe at home. We have studied the partial derivatives of the second partial derivatives of the Cobb-Douglas function. Do you remember that we were able to express the first derivatives in terms of the function? For instance, for this one would be alpha over x times the value of the function. You remember this representation? And this one would be beta over y times the value of the function, which is a very useful representation. It's possible to do something similar also with the second derivatives. So you should be able to express the second pure derivative with respect to x as some constant times the value of the function. The same for this one, and the same for this one. Try to do that by exercise. You would have squared of the variables in the denominator this time. It's very useful representation. We will, I mean, if you just try, we will see it later when dealing with the concavity of the Cobb-Douglas function. Conditions under which this function is concave. Okay. So this is the definition, mixed derivatives, pure derivatives. There are plenty of alternative notations for both the first derivatives and the second derivatives. So these are just examples, but there are more than this. So this is the usual one that we tried for the second derivatives, but we may also use a notation with two indexes here, which denotes the order of differentiation. So for instance, f12 means the first time it is differentiated with respect to its first argument, the second time with respect to its second argument. This is more useful when you don't want to call, for instance, the arguments x and y, but you have a more general structure, so you don't use this, you use this one. This is an alternative notation. Otherwise, instead of using the name of the function, we use the name of the variable. Sometimes we use the name of the function with the second here, or prime, depending on which order of differentiation we use. So there is plenty of notations, which most of the times they are clear from the context. Just be aware that we have many different ways to denote derivatives. Also, I want to recap the matrix notation for the first derivatives and the second derivatives. I already introduced the gradient of function f. Function f is a function of n variables, in particular 2. The gradient is a row vector that collects all the first partial derivatives with respect to the n variables. For instance, in the case of 2 variables, this is the gradient of function f. It collects the 2 partial derivatives with respect to x and y. More generally, we may have n variables. The notation for the gradient is this one, capital D f of x, where x is a vector, because we have n variables x, or this symbol here, which is a kind of reversed triangle, f of x, okay? So this d can be also denoted in this way. And for second derivative, these symbols will be squared. So it's very intuitive. For instance, we know that we have 4 second derivatives for a 2-variable function. We can put them in a matrix in which the position of the elements is clear. For instance, the row 1, 1, the position 1, 1 means a pure derivative taken twice with respect to x. Position 2, 2 is the pure derivative taken twice with respect to y. The mixed positions, and this is taken the first time with respect to x and the second time with respect to y, so it is position 1, 2, and this is 2, 1. What is the peculiar feature of this matrix that collects the second derivatives? It is symmetric. Why is it symmetric? Because of the Young's theorem, which is the theorem stating that the order of differentiation doesn't matter. So this second derivative, which is mixed, will be equal to this one. It is a symmetric matrix. Keep that in mind, because when we use the matrix of the second derivatives to approximate to the second order a two-variable function, we will have a quadratic form in which we have this matrix involved. This matrix involved. And this is a symmetric matrix. So what we will get is a quadratic form, because quadratic forms are defined for symmetric matrices. The matrix of the second derivative is called Hessian matrix of the function. It is also denoted in this way. So we may have this capital D or this symbol squared to denote the Hessian matrix. Well, this is just notation, basically. There is nothing difficult here. Here is an example. F of xy is xy squared plus the log of 1 plus x. I want to write down very quickly both the gradient and the Hessian matrix at the generic point xy, and next at the point 0, 1. Okay? They are derivatives, so they can be regarded as functions of the two variables x and y, but also as numbers whenever I compute them at a point. So the gradient is the vector of the first partial derivatives. So first position is with respect to x, so it is y squared plus 1 over 1 plus x. This is the first partial derivative with respect to x. With respect to y, it is what? These terms become 0. It is 2xy. Okay? What about the Hessian matrix? I have two partial derivatives. Take the first one. This is useful to fill the first row of the Hessian matrix, okay? Which means this term is this, again differentiated with respect to x, while this, now differentiated with respect to y, goes here. And the second element of the gradient will give rise to the second row of the Hessian matrix, differentiated with respect to x and with respect to y. Okay, so what is the second pure derivative with respect to x? It doesn't depend on y. Y is a constant, so it is minus 1 over 1 plus x squared. What is the second pure derivative with respect to y? You have to differentiate this with respect to y, which is 2x. What are the mixed derivatives? Okay, you can trust the Young's theorem and compute only one of them, and then fill also the other entry of the matrix. Or, in more complicated cases, you can compute, I suggest to compute both of them just to check your result, okay? I can compute either the derivative of this with respect to y, or the derivative of this with respect to x. Here I get 2y, and here I get again 2y. Is that clear? This is the matrix of the second partial derivatives. This is the gradient, or the row vector of the first partial derivatives. If I want to evaluate these quantities at a specific point, and that would be, for instance, important in applications, the gradient at the point 0, 1, x is 0, y is 1, is 2, this becomes 2, this becomes 0, while this one, evaluated at the point 0, 1, x is 0, so this is minus 1, y is 1, so this is 2, and this is 0. Okay? Okay, this is called gradient Hessian matrix, regarded as functions of x and y themselves, or gradient Hessian matrix at a specific point. just notation. Nothing new. Well, this is a repetition of the example we saw last time. Now, there is an important application of Hessian matrices, which is basically quadratic forms in two variables and their properties. And the next step would be approximating to the second order a two-variable function or an n-variable function. So this is the next part. So basically this is about concavity. Let me just show you a thing that I didn't say before. There is a very important particular number associated to any square matrix of any dimension. This number is called the determinant of the matrix. It is denoted in this way. You can always compute the determinant of a square matrix of any dimension. There is a general formula, and there are specific formulas for simple cases. For the 2 by 2 case, the determinant is given by the multiplication of the two elements in the main diagonal minus the multiplication of the two elements, the two remaining elements. Of course, if the matrix is symmetric, this is A to 1 squared, okay? Because they are the same element. So this is just the formula I need. The determinant, for the moment, just regard this as a number, a unique number which is associated to any square matrix. This is the determinant of A. Two alternative notation. This one, determinant of A, or A, written in this way. Like an absolute value, but this is not an absolute value, of course. Now, look at how the combination of few concepts, quadratic form, Hessian matrix, and determinant allows us to characterize concavity or convexity of two variable functions, and in general, more generally also of n variable functions. We will focus on two variable functions. I will give you then some hints on how to deal with 3 variables, 4 variable functions, but we will not use the properties of quadratic forms for larger dimensions. We will use quadratic forms only for 2 variables. So the characterization in terms of second derivatives only for 2 variables, because otherwise it becomes too complicated. Okay, so what is a quadratic form? We know already what it is. We have a symmetric matrix, squared, of course, n by n. We have a vector. Now we don't denote the elements of the vector as x1, x2, and xn. We denote them as h1, h2, hn. So we call the vector h. Why? Just because these will be vectors of increments, okay? We use h to denote the increment. Anyway, this is a vector of n variables. A is a symmetric square matrix. And we already know that this notation, H transpose times H times A times H, denotes a quadratic form in n variables. Okay, this was part of the previous slides. For instance, with n equal to 2, you already know this example. Okay, it is A11H squared 1 plus 2A12H1 H2 plus A22H squared 2. The only thing that changes here is the name of the variable. It's not x, it's h. But this is a quadratic form in 2 variables. This is the explicit Now this is the explicit representation. Extensive representation, and this is the matrix notation, okay? H transpose times A times H.
The box remains.
Yeah, it's bad network quality, but I don't know how to do. Let me just check if they can hear. What are they saying? Are they complaining about the quality of the network? Okay, can you hear me? How's the quality of the audio?
For me, everything's fine.
So it's fine. So okay, good. Thank you. Okay. So look at this. So these quantities depend on our matrix A, the entries in this matrix, and of course, they depend on H1 and H2. But these are given, these are numbers in our model, and these are variables, okay? They can vary because they are variables. So one very important question is, since the structure of a quadratic form is associated to the structure of this matrix, are there cases in which for any H1, H2, positive, negative, okay, you always get a positive number as the result for any H1, H2. I mean, these are numbers, A11, A12, A22. You can select, for instance, H1 equal to -1, H2 equal to 2, or H1 equal to -1/2, H2 equal to 7, or invert the signs, or both negative, or both positive. Are there structures of A matrix such that you can select any value of H1, H2, but you always get a positive result here, okay? After all, at least if A11 and A22 are positive, for instance, at least two terms here will be positive, okay? Clear? The other one will depend on the product between H1 and H2 and on the coefficient A12. So an important question is identifying situations in which whatever are the values that you select for H1, H2, positive or negative, you always get a positive result here. Another question associated is the same, but you always get a negative result here. And then the other cases in which the result is not a priori known, but it depends on the values that you select for H1 and H2. I consider only H1 and H2 positive or negative because if I select both H1 and H2 equal to 0, what happens to this quantity? If H1 and H2 are equal to 0, so this is, they are 0, 0, 0, the result is 0, okay? So a quadratic form computed at the point 0, 0 is always 0. We know that if we select H1, H2 equal to 0, the result is 0. But if we select at least one of the H, different from 0, are there conditions on the matrix by which we can predict what the sign of the result will be, whatever our choice is of H1, H2? And this is called studying the positive or negative definiteness of the quadratic form. After all, a quadratic form, I mean, it's useful to do that. A quadratic form can be also quadratic form in one variable, okay? This is a quadratic form in one variable. It's just the only way we can specialize that one variable is the coefficient A times H squared, not 1, H squared, because we have one variable, okay? Is this always positive, always negative? this is positive, no negative. When this is 0, the quadratic form is 0. It depends on the coefficient A. If A is positive, this is never negative. If A is negative, this is never positive. So it's very easy to study the positive or negative definiteness of a quadratic form in one variable. It's just a quadratic term. With many variables, this is not a number, this is a matrix. So already it's not easy to see what is the meaning of positive or negative. It is a matrix. And also, we don't have just one H, we have 2 or 3 or 4. So we are just extending, generalizing this result. We want properties on A, which will be a matrix, by which this will be always positive or always negative, but with many variables. And here are the definitions. This is in 2 steps. First, definitions. What means a definite, a positive quadratic form? What is a negative quadratic form? Second, we have conditions, definitions, and conditions for having a positive or a negative quadratic form. In the case of quadratic forms, we don't just say positive or negative. We say positive definite or negative definite, okay? But basically, positive definite means positive in the meaning of the one variable case, okay? It's just... So when we have a quadratic form in n variables that, for any possible choice of the vector h, of course different from 0, because otherwise it is 0, for any possible choice, it is strictly positive, we say that our quadratic form is positive definite. If it is always negative, we say that it is negative definite. If it is always non-negative, can be also 0. Can be also 0, not just when h is 0, but also in other cases. Anyway, it is non-negative. We say it is positive semi-definite. Semi-definite. When it is always non-positive, we say that it is negative semi-definite, okay? Different from the one variable case, in which the only case the quadratic form is 0 is when h is 0. For 2 variables, we may have cases in which h1 and h2 are not 0, but the quadratic form is 0 as well, okay? So we must distinguish between positive definite or positive semi-definite. And by the way, this is not a theorem, this is just a remark. Look at the red part, for instance. Negative semi-definite quadratic forms are the simplest possible example of concave functions. Positive semi-definite quadratic forms are the simplest possible example of convex functions in n variables. By the way, suppose that you want to find a value for h, which means h1 is 2, that minimizes the quadratic form in 2 variables. Okay? If your quadratic form, if you discover that your quadratic form in 2 variables is positive definite, this means that for any choice of h1, h2, it is always positive, okay? But when h is equal to 0, it is 0. So what is the value of h that leads to a minimum possible value of your quadratic form? It is 0. It is always positive. When h is equal to 0, it is 0. So the value that minimizes your function of n variables is 0, okay? So basically, a positive definite quadratic form, this is just an immediate consequence of the definition. A positive definite quadratic form, by definition, is minimum when h is equal to 0. A negative definite quadratic form, which is always negative, by definition, is maximum when h is equal to 0. Because when h is equal to 0, this is 0. Okay? Otherwise, it is negative. So, these are the most simple examples of functions that have a minimum or a maximum And also it's easy to show with, I mean, by analytical tools, but also graphically, that positive definite are the simplest examples of convex functions, negative definite of concave functions, okay? So these are the definitions, and what are the tools to understand whether a quadratic form is positive definite, negative definite, or correspondingly semi-definite? I mean, if there is also the case of indefinite, which is nothing, these do not apply, okay? So all the other cases is indefinite. What is the meaning of indefinite? For some values of h, you have a positive result, for some values a negative result. So it is indefinite. We can characterize each of these cases by just looking at the Hessian matrix. What is the meaning of the Hessian matrix? The Hessian matrix, by just looking at the matrix A that characterizes the quadratic form. So A is the matrix that characterizes the quadratic form. It is symmetric. We know that. If the two elements in the main diagonal, this one and this one, are negative, and the determinant of this matrix, which means A11 times A22 minus A21 times A12, is positive, then our matrix is negative definite, and the corresponding quadratic form is negative definite, and our function is strictly concave. Vice versa, if the two entries in the main diagonal are strictly positive, and the determinant of the Hessian matrix is again positive, this must be positive anyway. We have a positive definite matrix or a positive definite quadratic form, and our function is strictly convex. Then there are the corresponding weak definitions. Weak means that I replace the inequalities with less or equal to or greater or equal to if the two entries in the main diagonal are non-positive or negative or zero, and the determinant is non-negative, our quadratic form is negative semi-definite, which means concave but not strictly. If the elements in the main diagonal are positive or zero, and the determinant is again non-negative, we have a positive semi-definite quadratic form, which is convex but not strictly. Okay. I will finish the examples next time. I want to just give you some criteria for concavity, and next time already we start with optimization of concave or convex functions in one variable, okay? So we look at how to detect concavity or convexity first, and then look at the first order conditions, which means partial derivatives equal to zero, solving the system, finding the maximum or the minimum for our functions in some typical examples, some typical cases. I think we can stop here for today. If you can just look at the examples here and try to figure out, using this table, try to figure out why this examples 1, 2, and 3, and solve these examples 1, 2, and 3, that would be okay. But I will show you the answer of the exercises. I will solve this exercise next time. And also try to figure out why in the case of two variables we may have a negative definite is intuitive. It's like this. It's a kind of cup like this. Okay. Positive definite is a cup of coffee like this. Okay. Why negative semi-definite and positive semi-definite? How is it possible that there are situations in which a two-variable function is basically negative semi-definite, but there are many values of H1 and H2 by which it is zero, the result is zero, okay? Because this is the difference between semi-definite and definite. This is not possible for one variable function. Either you have a parabola like this or like this. You don't have a parabola in which you have for a certain interval zero, like this, zero, this. But you can have that for two variable functions. Try to figure out why geometrically. Okay, so these are examples of positive semi-definite quadratic forms. Okay, that's all. See you next time, which is next Thursday.
Bye, thanks.
Bye.
Thank you very much.
Thank
Bye.
you. Bye.
Bye. Thank you. Bye. See you next time, next week.